a, exercise type of lecture. So if you have some kind of blank paper, please take it out. So I'll be working on several problems together and derivations together. So you get familiar in applying the first law of thermodynamics. All right, so this entire class is how to use the first law of thermodynamics to quickly identify whether a process is, it's accepting heat, it's doing work on the system, or system doing work on the surrounding, it's temperature increase or decrease, internal energy increase or decrease, etc. So it's going to be the application of our first law of thermodynamics and everything we learned so far. I know my writing is sort of small, but those were just like a demonstration. Like if I were in your position, these are the things I would definitely put onto my equation sheet and know when and where to use them. So getting started from where we left over, that's isothermal expansion of gases. So in this kind of problem, right, so we're talking about the isothermal expansion of ideal gases, assuming only reversible PV work. Question asks you, how can you calculate or how can you represent the heat flow for this isothermal process? Like when we say isothermal, the temperature is not changing, but the heat or the heat transfer between your system and surrounding is not necessarily zero. So how do we calculate it? Now thinking about it, we start from an initial state. Let's say it's V initial, P initial, and some temperature. And it goes to a final state, which is V final, P final, some temperature, which remain the same. It's isothermal, so your temperature is not changing. And we know it's ideal gas. So what do we know from our equation sheet? Now, when temperature is not changing, my total internal energy is remain the same, because for ideal gases, your internal energy is only a function of temperature. Or the other way to put it is we know that delta U equals to 0 for ideal gases, isothermal processes. All right. What else do we know? We also have our work reversible, because it's reversible PV work, so we can use a W reversible equals to negative PdV to solve for the work that's being done in the process of the isothermal expansion. So here we have work equals to negative PdV, integral to each other. And in here, since we're looking at ideal gas law, your pressure equals to nRT over volume. And we can rewrite this expression as negative, V initial, V final, and then nRT over V dV. Now for isothermal processes, your temperature is not changing, N is not changing, R is not changing, so we can take everything out as constant. That becomes negative nRT, V initial, V final, 1 over V dV. You solve that integral, you get negative nRT ln V final over V initial. So far, so good. And then, calculating your heat transfer becomes quite straightforward. That's delta U minus W, which is nRT ln V final over V initial. All right. And let's take one step further of thinking about what's the physical meaning behind these expressions. Now, in this question, we're talking about the process being a isothermal expansion of gas. So when we read expansion, what we're saying is my V final is larger than V initial. Right, so it's an expansion. Your final volume is larger than your initial volume. And then when we're looking at the amount of work and heat transfer, we can derive more information. Now looking at the work, V final is larger than V initial, so this entire term is a negative term. So what does a negative work mean? Focusing on the system, we're talking about the system is doing work on the surrounding. All right, so that's the physical meaning behind a negative work, because we're focusing on the system. And then if we look at the heat, now heat is a positive value, meaning the surrounding is transferring heat into the system. All right, and this comes from reading the question of the system being an expansion. So we know that V final larger than V initial. And using the equation to derive an expression of work as a function of V final and V initial, you can predict whether your work is positive or negative, and heat as well. Yes?
So if heat is flowing into the system, how does it flow into the system? Does that matter?
It doesn't matter how it flows into the system. Just know there's heat transfer between your system and the surrounding. Yes?
So then the concept that heat transfer doesn't need to rely on a change in temperature, is that
Exactly. That's the whole point here. That's the whole point of doing this derivation. It's when we're talking about an isothermal process where your temperature is kept the same. It doesn't mean there's no work or heat transfer taking place. All right, so an isothermal process can merely mean your work that's being done by the system is the same number as the heat that's being transferred into the system. So as long as they cancel out, you can end up with the overall isothermal process. So that's the main misunderstanding. I want to make sure we're on the same page. So temperature change is not necessarily correlates to a heat transfer or not. All right, and alternatively, what if we have reversible adiabatic processes of a perfect gas? So we're going to do the same kind of derivation to see like what's going to happen for reversible adiabatic processes in a perfect gas. Like when there's reversible volume change, how does temperature change with respect to volume, or vice versa? So for this kind of derivation, it's always important to know like how do we set it up? Right, so in this case, we read the question and write down or translate these wording into like mathematical equations that we know. For example, when we say reversible, what do we know? Like reversible PV work only. So that gives us the dW reversible equals to negative PdV. Adiabatic, so that's the word that we use whenever there's no exchange of heat between your system and surrounding. So adiabatic process, by definition, we're saying there's no heat transfer. So dQ equals to 0, and consequently, your overall heat transfer also equals to 0. And when we have perfect gas or ideal gas, what we're saying is the PV equals nRT. Your internal energy is only a function of temperature, or you can rewrite du equals to Cv dt. And on top of all these terms, we have our first law of thermodynamics, which is du equals to dw plus dq, first law. So for the rest of my class, I'll always assume we have like a closed system at rest and no external field. I'll also put that in a clear mark whenever you have an exam. I'll say like unless otherwise specified, we can assume the system is closed. It's at rest and no external field. All right. So now we have all of these things. What we're trying to do here is to find out a relationship between your temperature and volume when they're changing. So how do we get started? All right, so if we think about it, we can start from our first law of thermodynamics, and by plugging each of the terms, like what is du, what is dw, what is dq, into my first law of thermodynamics. So in here, using the ideal gas, what we know that du equals to Cv dt. On the right-hand side, we know that dq equals to 0 for the adiabatic process, and my dW reversible equals to negative PdV, or let's say negative nRT over V dV. All right. And then we can move the terms. So when we're looking at these kind of equations, you want to move my temperature, go to with my dT, want to remain like volume with respect to dV. So later on, when we're taking the integral on both ends, we have a mean to do that normal integration. So now we're just moving the terms in this expression. And what we end up getting is Cv over T dt equals to negative nR over V dV. And then taking the integration on both ends, we got, well, Cv over T dt between T1, T2 equals to negative nR over V dV from V1 to V2. And that's how straightforward the integral calculus I expect you to know, right? Just like integration of 1 over x dx. And solving this integration, we end up having an expression of Cv ln T2 over T1 equals to nR ln V1 equals to V2. Note that this negative goes in there. That's why it's V1 over V2 in the right, on the right-hand side. Or if we're putting everything back into the logarithm, into the natural log, we can write it as like natural log of T2 over T1 to the power of Cv equals to natural log of V1 over V2 to the power of nR. Or the other way to put it is something inside my natural log are equal to each other. So we can end up getting the expression of T2 over T1 equals to V1 over V2 nR over Cv. Yes?
Oh, so in the integral, I guess like line, we take the integral of 1 over the variable, but then somehow we end up with T2 over T1 and then V1 over V2.
Okay, so this V1 over V2 comes from the negative side.
Oh.
So it's like negative ln V2 over V1, but we're putting the negative inside there.
Thank you.
Any other questions? So the idea here is very straightforward. Like what we start from are just definition of all the terms and then first law of thermodynamics. And by using our first law of thermodynamics and also what we know about the definition of these terms, we find out that for any adiabatic processes of a perfect gas, your temperature and volumes are connected to each other. The change of your temperature you can predict by observing the change of the volume and vice versa. All right, so thermodynamics is a topic that we use our knowledge to link terms that we can measure, we can experimentally measure. And these are the things you can set up experiments to validate our derivation. Yes?
If we're ever given the scenario on the test where there was like a perfect gas and is adiabatic, would we have to go through like the entire steps of showing neutralization, or would you just...
Yeah, so that's a very good question. So for the purpose of test taking, you do not have to show the derivation unless we specify to so like, hey, start from the first law of thermodynamics. First, demonstrate the relationship between T1, T2, and V1, V2. And maybe there's a second part of applying that equation. But if we didn't specify it, you do not need to start from the derivation.
How did CV and NR get to be like exponents?
Well, so this is the natural logarithm. So whenever you have a product times the natural log, you want to move that constant inside to the natural log, it goes on to the power. All right, so we're ready to start and applying these things in a more like faster setup. So far we went over, again, like first law of thermodynamics, we went over state functions, heat capacities, work, and heat. So now let's get started in applying them in a very fast setup. But before we do that, let me just give you a quick summary in what we covered this entire quarter. Like we covered all these concepts, right? But how do we translate the wording to like mathematical equations? Like how does that translation takes place? So there are several thermodynamic processes, and there are several thermodynamic quantities that we discussed. So a thermodynamic process basically tells you how a transformation takes place. There are all of different kind of them, so we're going to go through them one by one. So starting from like what we call a cyclic process. So when we say a cyclic process in thermodynamics, we're saying the initial state and the final state are the same. So what do we know whenever you see a cyclic process? Remember, we have state function versus line integral, right? So when we have a cyclic process where your initial and final thermodynamic state are the same, we say that all of our state functions will have no overall changes. Or what are the state functions we know so far? We have internal energy, we have enthalpy, we have volume, temperature, pressure. So all of these state functions will not change. Or the overall change of my state function. So whenever you see like delta, so this symbol just tells you that's final minus initial. So a delta U equals to 0 doesn't mean you don't have like du or infinitesimal change of internal energy throughout the way. What we're just saying is like from your initial and final state, everything adds up to be 0. So remember our cyclic process example that we did. You have 1, 2, 3, 4, 4 different steps. For all those 4 steps, you can calculate delta U for each step. But those 4 delta U will add up to be 0 for that cyclic process. All right, so that's the first one. Second one, reversible process. So when we look at a reversible process, we're effectively saying the system is always infinitesimally close to equilibrium, or only infinitesimal changes are taking place. So when you read a reversible processes, we basically in this entire chapter, we're saying like dW reversible equals to negative PdV if we're only considering PV work. All right, so for reversible PV work only processes, we can use dW reversible equals negative PdV to solve for the work that's being done for that process. In our next chapter, we'll introduce another concept of dQ reversible. That equals to the TdS. So temperature times the infinitesimal change of entropy. So that we'll discuss in chapter 3. All right. And then for next one, we have isothermal processes. So isothermal, constant temperature. And for ideal gas only, we know that the internal energy or enthalpy are constant. Next one is something you should know. For adiabatic processes, which of our thermodynamic quantity is something we know? Q, right? So dQ equals to 0, Q equals to 0. So basically, these are the things like, I don't expect you to memorize, but you really should get familiar with it. So when reading the problem will only say like, okay, you have an adiabatic expansion. So you need to be able to translate that adiabatic expansion into like dQ equals to 0, Q equals to 0, and V final minus V initial is positive. So that's my expectation to you. And next up, we have 2 more, which is isochoric and isobaric. So isochoric, constant volume. Right, so what does constant volume mean in this chapter? So remember, we have W reversible equals to negative PdV. If we say a isochoric process with reversible PV work, then you can quickly derive, okay, so for reversible PV work only, isochoric process, volume not changing, my work equals to 0. And then for isobaric processes, in this entire chapter, we only discuss like delta H, the physical meaning of your enthalpy change equals to QP. And we'll discuss more about QP in later chapters. Yes?
Can you think of an example of an isochoric process that has not PV work?
Yes. Okay, so the question is, can you think about the process that's isochoric but no PV work? But on top of PV work, the other kind of work you have maybe electric work.
Okay.
Right? So you can connect it with like an electric wire, and there's electrochemistry going on, and electrons are flow around, but no PV work is being done. So PV work is basically like expansion or contraction. We can have a chemical reaction taking place at the constant volume. So as a chemist, we normally don't care about PV work that much. So later on, when we talk about Gibbs free energy, we'll have more discussion in like, okay, what exactly is like Gibbs free energy, and what exactly is Helmholtz work energy? I'm jumping too far away, but nevertheless, there are other kind of work that's available out there. All right. So with that in hand, we're gonna jump into a small marathon. So here we have A, B, C, D, E, F, G, H. We have 8 different problems. So we'll do them all together. I'm gonna keep the question here out, and you please take out a piece of paper, and we'll work with you on Blackboard together. Like quickly derive in these scenarios. It's telling us for each of the following process, can you deduce whether each of the quantities Q, W, delta H, and delta U, so 4 different thermodynamic quantities, quickly derive if they are positive, 0, or negative, right? So the physical meaning behind these properties is pretty straightforward. A positive work means the surroundings doing work on your system. Negative work means your system doing work on the surrounding, right? So how can we quickly predict what is happening? Like how does these thermodynamic quantities change? So we'll do that together. You have enough things, and I've been putting these things on the top, and we also went over how to translate each processes into equations. So I'm gonna leave it there, and we'll do it one by one. First one, okay, we have reversible melting of solid benzene at 1 atm and normal melting point. And I'm telling you that my density of benzene is larger than the density of your liquid benzene. And it's a melting process, so we know that melting takes energy. So, getting started. And if you're watching the recording, I know you are not, but for anyone who's watching the recording, you'll see the workout solution in the annotated notes, so you can check it out yourself. First question. We have reversible phase change or melting at constant temperature and pressure, predicting how does Q, W, delta H, and delta U change. So in this case, we're looking at melting. So something we can quickly write out is melting is a process that takes heat. So it absorbs heat from the surroundings, so the melting can take place. So we already have like Q that's soft. So what about W? So since melting itself is like a super slow process, if we're considering the PV work that's being done, then we have a reversible PV work. So that equals to negative PVV. And that's equals to negative. My pressure is constant. It says the reversible melting of solid benzene at 1 atm and normal melting point. So we specified a pressure being constant for that process. So we can take my pressure out, and we have P final minus, B final minus P initial. Right. So what are my volume? We know that my density of my solid benzene is larger than the density of my liquid benzene. It's melting, so my final volume is my liquid my initial volume is my solid. So which one of them is smaller or bigger? So my final is liquid. So my final is going to be a larger number. So this one will be a positive value, because final minus initial get a positive value, but your overall work is a negative value. But it's going to be a very small number, because again, the melting process, your density change is like very small. So we're going to put small here. Yes?
Why is it important to know that it's at the normal melting point?
It's not. We just have to specify some kind of temperature. It's convenient to say like normal melting point. Okay, so that's one. And also we specify it to be at normal melting point. It's like you have 1 atm at normal melting point. It basically says your liquid and solid are in equilibrium with each other, so that melting process is taking place, but at a very slow rate. So if the temperature is like really high, then we might look at a non-equilibrium process. It's overcomplicating the matter. Yes?
For the work, can we think that the surrounding, like the different temperature, is doing work on the system so that the work has to be negative?
Right, but it's a very small number, right? So your volume is like shrinking. So the surrounding is doing a little bit of work onto your system, but at a very small number. Okay, so we have Q, we have W, and then thinking about what is my delta H. Now, delta H equals to QP. That's the physical meaning of the change of enthalpy. That's the one we just went over. So we know that QP is a positive number, so that's positive delta H. Now, what about delta U? So delta U equals to my QP plus W. Now, my W is a negative yet small number, but my QP is a significantly larger number, so it must be a positive as well. So not doing any calculation, it's more or less just quickly set up and translate these wording so you know how does your heat change, how does the work change, how does the internal energy and your enthalpy change. All right? And for problem B, the question is pretty much the same. Question B is saying we have reversible melting of solid benzene at 1 atm at normal melting point. Wait, question B is reversible melting of ice, sorry. Reversible melting of ice at 1 atm at 0 degrees Celsius. So again, it's a reversible melting at a constant temperature and your normal melting point. So it's pretty much equilibrium with each other, a reversible PV work under consideration. But for ice, there's something we know, that the density of ice is smaller than the density of water. Right? So the only thing different is my work in this process. Because in this, yes?
Sorry to interrupt. I was just thinking for like our equation sheet that we made, how many things should we know like that? I know that's pretty straightforward, density of ice is less than water.
These are the things we'll give you. Like if I'm asking this question in the exam, I'll tell you how does the density change. Like the same applies to the first one. Right, but with this information in hand, and then we're ready to say, okay, so my Q must be positive for melting. My work, again, is a negative P V final minus V initial. But now my V final minus V initial is a negative number, so this becomes a positive value. And then everything else is positive. So the kind of question you'll see on the exam is I'll give you a process, let's say a reversible adiabatic expansion of a ideal gas. And I give you like 4 different blank space and tell me how does your Q, W, delta H, and delta U change. Later on, you might also encounter questions like how does delta G, delta A, delta S change. But nevertheless, so these are the kind of questions. I'm just doing this as an example in what do I expect you to know. Okay. Next one. Reading it, we have reversible adiabatic expansion of a perfect gas. So problem C. Problem C. Well, we have reversible. So that tells us we have dW reversible equals to negative PdV. Adiabatic, we have dQ equals to 0, Q equals to 0. And expansion tells us V final is larger than V initial. Perfect gas, we have PV equals to nRT, U is only a function of T, etc. So several things, right? We're looking at Q, so this one is already solved. We know that Q equals to 0. And in here, and then from here, you have different ways you can solve it. You can start by solving W, or you can use the equation we just derived. So using the relationship we just derived for the adiabatic processes, we have T final over T initial equals to V initial over V final NR over CV. And in here, we know that V final is larger than V initial, so my T final is smaller than T initial. All right, so in the process of an adiabatic expansion, when volume is increasing, my temperature must be decreasing. And consequently, we know that my internal energy is only a function of temperature, or my delta U actually equals to CV dt from T initial to T final. And we can get that to be CV T final minus T initial. So my delta U must be a negative number. Yes?
If we hadn't just derived that relationship, what would we do?
Well, you can also solve the work that's being done for the process, or you have to start from the derivation, right? It's an adiabatic process. You can do what we just did and to get this relationship. But if the question only asks you to solve for whether like dQ, W, delta U, and delta H are positive, negative, or 0, you can use that relationship directly. So we have delta U as a negative number. Now for my delta H, that's the same idea. We have T initial, T final, Cp dt. And my Cp just equals to Cv plus Nr. It doesn't matter, it's always a positive number. T final minus T initial, also a negative number. So in this whole process, we end up having, okay, so work must be a negative number. So far, so good? Okay, so let's move on to next one. And next one, I'll give you some time to work for it. And at the same time, I'll also work it on the board, but I'm not gonna talk about it. So, and then after like 5 minutes, we'll check our answers together. Okay, so next question. We have reversible isothermal expansion of a perfect gas. So let's work on it together. Do you have the same answer? So the best way to put it, like, you don't have to always start from work or always start from Q. It's more like by reading the question, you can start by assigning things you already know. Like adiabatic tells you Q equals to 0. So this question, we have isothermal processes for ideal gases. So for ideal gases, we know these are internal energies and enthalpies are only dependent on temperature. So for isothermal processes, it's quite obvious. We have delta U equals to delta H equals to 0. All right. And then thinking about how to solve for work and heat. There's an expansion. It's reversible PV work expansion. So we have W reversible equals to negative PdV integral together. And since we know that it's an expansion, V final is larger than V initial, that's how we derive this entire work being negative, meaning your system didn't work on the surrounding. And then, using the first law of thermodynamics, we end up to get Q equals to a positive number, because they must add up to be 0. Any of you get to the same answer with different method? No? Okay. Nevertheless, it's, it doesn't matter what method you get, but as long as we get to the same conclusion, you're using the laws of thermodynamics correctly, that's all we want. All right. Ready to move on to the next one? Okay, next one. Adiabatic expansion of a perfect gas into vacuum. So, this one, again, we'll read it. What do we know? We have adiabatic expansion. So adiabatic tells me my Q equals to 0. We're expanding a perfect gas into vacuum. So this is our Joule experiment setup. All right, remember, it's adiabatic expansion. You start from a cylinder of gas. You have a valve, you open it up, and then that gas slowly expand into vacuum. So in this whole process, you cannot use the work reversible equals to negative PdV because it's an irreversible process. But in that cylinder, your gas is not doing any work on the surrounding. It's just expanding into the vacuum. So we have work equals to 0, and my delta U must equal to 0, and delta H also equal to 0. That's our Joule experiment setup. All right. And then we have our Joule-Thomson adiabatic throttling of a perfect gas. So these two are almost the same kind of application. We went over this experiment in class. We say it's a constant enthalpy process, meaning my delta H equals to 0. And since it's delta H is only a function of temperature, right? So if delta H is 0 and we're dealing with ideal gases, my delta U must always also equal to 0. It's adiabatic, so we have Q equals to 0. So the total work that's being done also equals to 0. Yes?
Do you explain what throttling means again?
So this basically is the experiment that we did for the Joule-Thomson experiment. Remember, on the left you have a piston. On the right-hand side you have another piston. You have a chamber of gas slowly moving, right? So the left piston is doing work on the gas, and then the gas passes through a center like filter or something, and that gas continues to do work on the right piston. So that process is called throttling. You'll only see that in the Joule-Thomson experiment, in this class at least. Yes?
Can you explain why work equals to 0 again?
So in this one?
Just
Okay, so in this one, in the Joule-Thomson one, we started by, remember, like we did that derivation together to demonstrate that the Joule-Thomson experiment is a constant enthalpy process, meaning delta H equals to 0. And the logic behind that delta H equals to 0, meaning my temperature must maintain the same, because my delta H is only a function of temperature for these ideal gases. right? Then my internal energy change must also be 0. Then for the entire adiabatic process, we derive that Q equals to 0, and hence your W must equal to 0 due to our first law of thermodynamics. Yes?
So if delta H equals to 0, then delta U also equals
For ideal gases. So the logic is for ideal gases, both your enthalpy and your internal energy are only function of temperature, right? So if one of them is not changing, it's telling us the temperature is not changing, then the other one must also not be changing. But for ideal gases only. All right. And then moving on, we have 2 more questions we want to do together. This one is reversible heating of a perfect gas at constant pressure. So, again, reading this question together, when we say reversible heating of a perfect gas at constant pressure, what do we have? So this tells us my final temperature is larger than initial temperature. It's at constant pressure, so we can start from my delta H equals to QP, and my delta H equals to my T initial to T final Cp as a function of temperature, Cp dt. And this term must be a positive number because my heat capacity is positive, and then my dt, my final is larger than my initial. So my change of temperature is positive, so my delta H and QP must both be positive. Yes?
Sorry, I'm confused. If it's cooling, why is the final temperature higher?
This one is heating.
Oh.
Cooling is the next question. All right. And then, next step, we have delta U. Well, delta U is the same idea, right? Temperature is increasing. It's only a function of Cv dt. You take the integral. Temperature is increasing, Cv positive, so delta U must be positive. All right. And for work reversible, so this one we have to specify is reversible PV work. Well, it's reversible, but we want to say specify PV work only. Now for work reversible, that's equals to negative V initial, V final, PdV. My pressure is constant, so I can take my pressure out. So negative pressure. And my V final minus V initial. And for ideal gases, we get my volume equals to nRT over pressure minus nRT over pressure. Because my pressure and pressure will cancel out. And we get negative nR times T final minus T initial. So since my T final minus T initial is positive, my work must be a negative number. All right. So for this kind of question, we can also translate it into like a true and false problem. Like we could say, in a reversible heating of a perfect gas at constant pressure, reversible PV work only, the system is doing work on the surrounding, right or wrong, right? So like these are the kind of alternative way will ask the same question to you. All right. And one last example together. Just clean out this one. Okay. Very good at it. Okay, last example. We have reversible cooling of a perfect gas at constant volume. So this one, again, reading the question, we can write out my T final is smaller than T initial because it's cooling. Constant volume, my change of volume is 0. And it's reversible PV work, so W reversible equals to negative PdV. So for this problem, the first thing we can write down is my work reversible equals to negative PdV equals to 0, because my volume is not changing. It's isochoric process. And then, secondly, we can write my delta U and delta H are both decreasing because my temperature is decreasing, or T final is smaller than T initial. And in this process, my delta U also equals to QV, which equals to 0. So your heat, heat is negative. Yes.
Experimentally, how would you heat a gas and keep the pressure constant?
I'm not an experimentalist, I'm sorry. But I mean, you can think about something. So your question is, how can you heat the gas with the pressure constant? Or is that your question? Right, but if you just heat it at atmosphere, then as long as you keep the pressure inside your container and the pressure of the outside atmosphere at the same, it's constant pressure. So we encounter more constant pressure process than you imagine. Like if you have a chemical reaction like open to air, it's at constant pressure. It's always like atmosphere pressure. With me so far? Sort of. Any other questions here? So this lecture is a quick summary of our entire chapter 2, where we introduce our first law of thermodynamics. We went over definition of all the terms. We went over different thermodynamic processes, and then end this entire chapter by applying these thermodynamic terms in different thermodynamic processes and quickly predicting how these quantities are positive, negative, or 0. And in our next chapter, we'll move on to talk about entropy, which is a lot more fun. This lecture is also fun. I like entropy. But nevertheless, so we're moving on to entropy in our next lecture, and hopefully I'll be on time, but I'll see you next Monday.